Hello viewers, myself Dr. Mahantesh K. Welcome you to this pre-recording sessions on Introduction to Electromagnetic Waves. Module 1, Class 3. Now that we have formulated a new language in our previous videos, we shall establish a few basic principles of electricity and attempt to describe them in terms of electricity and electric charges. So the main agenda in this video, I'll be revising some concepts of coordinate systems, especially on spherical coordinate systems, followed by Coulomb's law and introductory concepts on electric field intensity. So a quick review on the spherical coordinate system consists of rho phi theta as coordinates. Rho is in the direction of radius. Phi is an angle called as azimuthal angle, which has been created with respect to x-axis and the line joining the origin and point P. And theta is the other coordinate axis in spherical coordinate system, can be obtained with respect to z-axis and the line joining the origin with respect to point P again. So what are the differential surface units of a spherical coordinate system? With respect to a radius, with respect to azimuthal angle, it is dr r d theta normal to phi. With respect to theta, a surface which is normal to theta can be given as r dr sine theta d phi. With respect to the radius r, normal to surface radius r d theta r sine theta d phi. So differential volume exists in terms of dr, r d theta, r sine theta and d phi. We can observe differential surface units are a vector quantity, differential volume units are a scalar quantity. Relation between the rectangular and the spherical coordinate systems, we could draw the relationship between rectangular and spherical coordinate system in terms of r can be calculated as its magnitude of x, y, z. Theta cos inverse of magnitude of x, y, z varies from 0 to 180 degree. Phi tan inverse of y by x, and phi varies from 0 to 2 pi, that is 360 degree. Whereas x and y, z of Cartesian coordinate systems can be calculated using the equations given as in the table. And also you can note what is the dot product of unit vectors in spherical and rectangular coordinate system is given as in the table. So this was the example which you have done in a previous video. So we have found the spherical coordinates of C and the rectangular coordinates of D. C was given in rectangular coordinate system and we have calculated the coordinate values of a spherical coordinates, and D was given in spherical coordinate system. We have obtained the values of coordinates in rectangular or Cartesian coordinate system using the following equations. Okay, so now in this video we'll start with Coulomb's law and electric field intensity, which is an actual part of your syllabus in VTU. So records from at least 600 BC, it shows the evidence of the knowledge of static electricity. The Greeks were responsible for the term electricity, derived from their word called amber. So Dr. Gilbert, a physician to Her Majesty the Queen of England, was the first to do any true experimental work with this effect. And in 1600, he stated that glass, sulfur, amber and other material which he named would not only draw themselves straws and chaff, but all metals, wood, leaves, stone, earth, even water and oil. It was very surprising. Shortly thereafter, an officer in the French army engineers, Colonel Charles Coulomb, performed an elaborated series of experiments using a delicate torsion balance and invented by himself. You could see the delicate torsion balance here, which was invented by himself, Colonel Charles Coulomb, to determine quantitatively the force exerted between two objects. Now we shall try to understand the force exerted due to a charge on another charge or another number of charges. So his published result is now known to many high school students as well as engineering students and bears a great similarity to Newton's gravitational law discovered about 100 years ago. So Coulomb stated that the force between two very small objects separated in a vacuum or a free space with a distance d, which is larger compared to their size of charge, is proportional to the charge on each and inversely proportional to the square of the distance between them. I repeat, Coulomb stated that the force between any two very small objects separated in vacuum is directly proportional to the charges Q1 and Q2 and inversely proportional to the square of the distance between them. So here you could see Q1 and Q2 are positive or negative charge quantities. R is the separation and K is a proportionality constant. So what is K? K equal to 1 over 4 pi epsilon naught. The factor 4 pi will appear in the denominator of Coulomb's law, but will not appear in the more useful equation, including Maxwell's equation in future. So epsilon naught is the permittivity of free space epsilon is measured in terms of Faradays per meter and has magnitude of epsilon naught in free space. Epsilon r is equal to 1, so epsilon naught will have a value of 8.854 into 10 power minus 12 farads per meter. The quantity epsilon naught is not dimensionless. Coulomb's shows that it has the label Coulomb square or Newton meter square. So now Coulomb's law can be stated as F, which is a force acting due to charge Q1 on Q2 or Q2 on Q1, is equal to 1 over 4 pi epsilon naught Q1 Q2 by R square. The force F acts along the line joining the two charges. It is repulsive if the charges are alike in sign and attractive if they are of opposite sign. You could see here, if you have two positive charges Q1 and Q2, there will be a repulsion of force. There will be a repulsive force. Whereas if you have opposite charges like Q1 and Q2, which is shown in the second half of the figure or the diagram, which will have an attractive force. The experimental law of Coulomb. So here we are going to represent the Coulomb's law in terms of a vector. Suppose Q1 and Q2 are two charges separated by the distance R12. Now Q1 is represented in terms of its position vector R1, small r1, Q2 with respect to its position vector R2, then the distance R12 or vector R12 in the direction of F2, in the direction of Q1 to Q2 is given as R2 minus R1. In vector form, the Coulomb's law is written as F2 is equal to 1 over 4 pi epsilon naught Q1 Q2 by R12 square in the direction A12. So what is A12 here? What is this A12 doing here? It's a direction. It represents the direction of a force acting on Q2 due to the charge Q1 in the direction 1, 2. So F2 is the force on Q2. For the case where Q1 and Q2 have the same sign, while A12 is the unit vector in the direction of R12, the line segment from Q1 to Q2. So what is A12? A12 is the unit vector which represents the vector R12 to its magnitude, vector R12. They are also given as R2 minus R1 over magnitude of R2 minus R1 in terms of position vectors. Let us take up an example. Say a charge Q1 is equal to 3 into 10 power minus 4 coulombs is placed at the point M 1, 2, 3 in a rectangular coordinate system, and a charge of Q2 equals to minus 10 power minus 4 coulombs is placed at N is equal to 2, 0, 5. Both are located in a vacuum. So now you have to calculate the force exerted on Q2 by Q1. Okay, so it is from Q1 to Q2. So I will consider R12 as a vector which is equal to R2 minus R1, can be given as in coordinate system 2ax plus 0ay. Why? Because I don't have the ay component plus 5az minus, this is at location M, 1ax plus 2ay plus 3az, and we'll obtain 1ax minus 2ay plus 2az. Now I'll calculate the unit vector which represents the direction. A12 is equal to vector R12 divided by magnitude of R12, which gives 1 over 3ax minus 2ay plus 2az. So now force is given as F2 is equal to, that is force exerted on Q2, I'll represent it as F2, equal to 1 over 4 pi epsilon naught Q1 Q2 by R12 square into A12. This is derived from Coulomb's law. So now I'll substitute all the values given in the question. So this is how it looks, and I'll obtain the value as minus 10ax plus 20ay minus 20az newtons. What is F1 then? F1 is equal to minus of F2. If you're trying to calculate the force exerted on Q1 due to Q2, it will be F1 equals to minus F2. So it is force exerted on Q1 due to Q2. F1 is equal to minus F2. And you'll obtain the negative answer of this F2. Now let us try to concentrate on electric field intensity. So if we now consider one charge fixed in a position, say Q1, and move a second charge slowly, okay, move a second charge slowly around. So we note that there exists everywhere a force on this second charge. Force on it is given by Coulomb's law, that is Ft on a test charge. Ft is a test charge which is moving around Q1. So Ft is equal to 1 over 4 pi epsilon naught Q1 Qt by R1t square A1t. So now, if I would like to calculate the force exerted per unit charge, per unit test charge, I can take this Qt to the denominator. When it is moved to the left hand side, it appears to be in the denominator. So this is a force exerted per unit charge, per unit test charge. which is equal to 1 over 4 pi epsilon naught Q1 by R1T square A1T. So this is called as electric field intensity. Now, the quantity on the right hand side of the equation is a function of only Q1. And the directed line segment from Q1 to the position of the test charge describes a vector field and is called the electric field intensity. Now we define the electric field intensity as the vector force on a unit positive test charge. So electric field intensity E is measured by unit newtons per coulomb or volts per meter, and it's given as E is equal to F over Q is equal to 1 over 4 pi epsilon naught Q1 by R1T square of A1T. So this is a simple representation of an electric field of a single point charge. So if you assume a point charge, electric field equation can be written as E is equal to 1 over 4 pi epsilon naught Q by R square in the direction AR. So AR is a unit vector which represents the direction from the point of a charge to a point charge is located to the point at which E is desired to be measured. So this is a representation, a vector representation of an electric field intensity for a given charge Q. And Q is at the distance of x dash, y dash and z dash from the origin. Whereas I'm trying to measure an electric field here at this point P. So this P is at the distance of R, where R is equal to R minus R dash in terms of position vector. And this is the electric field intensity at this point P of x comma y comma z can be measured in terms of 1 over 4 pi epsilon naught Q over R minus R dash square into AR. AR can be represented in terms of R minus R dash over magnitude of R minus R dash. So this R minus R dash and this magnitude of R minus R dash square into magnitude of R minus R dash becomes R minus R dash cube magnitude. I could simply write this equation as x minus x dash ax plus y minus y dash ay plus z minus z dash az over x minus x dash square plus y minus y dash square plus z minus z dash square whole to the power of 3 by 2. Therefore, the electric field intensity due to 2-point charges, say Q1 at R1, Q2 at R2, is the sum of the electric field intensity on Q2 caused by Q1 and Q2. Suppose if we want to measure a total electric field intensity at this point P due to Q1 and Q2, it is simple summation of both the charges, both the impact of charges of Q1 and Q2 both. So it should be the simple summation of electric fields E1 due to Q1 and E2 due to Q2 in the direction A1 and in the direction A2. So this is just an example problem where a charge of Q1 2 microcoulomb is located at a point P1 in the origin 0,0,0 and a second charge of 3 microcoulomb is at P2 minus 1, 2, 3. Find the electric field intensity at M 3, minus 4, 2. So carefully observe, we have 2-point charges here. One is Q1, the second one is 3 microcoulomb at P2, and you need to find what? Electric field intensity at the point M. So now I will consider R minus R1 with respect to Q1. So I would get 3AX minus 4AY plus 2AZ. Magnitude of R minus R1 is square root of 29. And with respect to P2, 3 minus 1, that is 3 minus of minus 1 is 4, 4AX, minus 4 of minus 2 is minus 6AY, 2 minus 3 is minus AZ, and magnitude of R minus R2 is equal to square root of 53. I'll be substituting. Why? Because the electric field at point M would be the summation of electric fields due to the charge Q1 as well as charge Q2 at two different points, P1 and P2. Can be given as 1 over 4 pi epsilon naught Q1 by magnitude R minus R1 square A1 plus 1 over 4 pi epsilon naught Q2 by R minus R2 square, magnitude U and A2. And now it's a simple math. Just substitute all the values of given charge as well as the location and magnitude values which are computed, and you shall be getting this answer, that is 623.7 AX minus 879.92 AY plus 160.17 AZ volts per meter. Don't forget this unit value in SI system. So it is electric field intensity due to 2-point charges located at P1 and P2 on M, which is located at 3, minus 4, 2. So thank you for watching this video. I hope it was useful. So we have introduced Coulomb's law and electric field intensity. Now things will become little complex and more interesting to study, like what is the behavior of electric field intensity in terms of flux density, and we'll introduce a couple of laws in between and just try to move or try to understand the dynamicity of the charges. So thank you for watching this video. Take care.